Hello, welcome to the EasyCFD video, Computational Fluid Dynamics Introduction. First I'm going to get into Citrix. I have an icon right there. It may be a little tougher for you. Uh, Go to USMMA Marine Engineering Apps. And then we just have to wait. And there we go. Great, it's there. That was quick. And typically you lose the mouse, the arrow, but if you just click on left click, it should find your arrow again. So we go to EasyCFD right up there, double click on that, and it should take us into the EasyCFD. First thing you need to do is to make a tunnel, a wind tunnel, a virtual wind tunnel, and use this rectangle tool here. Click on that, and I'm just going to take up quite a bit of the screen here, and you make something that looks kind of like this. Okay, there we go. So each one of these spaces is about 0.7 meters, so this whole thing must be about 1, 2, 3, I don't know, 7 or 8 meters. All right, so leave it on snap and show, and 0.1 for the size, 0.1 meter for the size of each one of these little rectangles. You shouldn't have to mess with that. So first thing we're going to do then is the next thing we're going to do is import the geometry of the airfoil. So go to import geometry, point data, click on that, and then go wherever you stored it. Hopefully it's something that you can access. So I'm just going to scroll down here. Keep going. There it is. It's going to be this one, NACA 0012C. Okay, that's what I'm going to send you. And hit OK, right? And there it is. Came right in. And then we're just going to click on Import Data. And there it is, right smack in the middle of our wind tunnel, right at where the red lines meet the origin, right? Incidentally, you can, when you move the mouse around, it gives you X and Y coordinates up here, rather X and Z. Z is up. So the first thing I want to do is I need to place it in a block. First you highlight it with the cursor, then you go to a new, okay, hit new, and then it made a new block for you. Now just hit transfer, and we transferred it. There we go. So the next thing we want to do is we're going to move this thing closer to, we're going to have the wind coming in from the left here, the air coming in from the left, and so we're going to move it closer. It's better to leave more room downstream to let the wake develop. So I'm going to move this first. So let's move it. So I highlight it again. I'm going to hit transform here. And then we're going to click move up there. Don't forget to do that. Translation. And going to move it negative, let's say 2 meters probably is probably good. And make sure we don't want to move it in the Z, so make it 0. And first we're just going to preview it and look at it. That looks perfect, and apply it. And there it goes. So now I just want to do one more thing, is I want to just alter its angle of attack to maybe 4 degrees. So highlight it again, transform one more time, and then hit rotation here. And angle, let's make it 8 degrees. And we're going to pick the rotation center, so the point about which it's going to rotate, just somewhere right there in the middle. It's not that critical. And let's preview it first. So I need a negative 8. That would have worked fine, but preview. And there it is, and we apply it. And perfect. Now I just want to make it, yeah, that's fine, that's fine. Yeah, the tunnel really needs to be bigger, like it needs to be really further away from the walls, but for instructional purposes this will be fine, and probably need even more room downstream. Now we're going to mesh it. We're going to make a mesh around it. So I'm just gonna, I think the target number of nodes ends up being 57. If you zoom in on this thing here, you'll be able to see, I just hit each one of these little red points is a node. So the target number is 57. So if you put more of them, it'll make a finer mesh. Let's just stick with what we have here, because otherwise it'll take too long to run. And stick with the 57, no need to change it. And we're just going to hit compute now, and it'll make the mesh. So it takes a little bit. and it's telling you the number of elements that are happening. Okay, so there we go. We've got 3,810 elements. In other words, the area is enclosed by the grid. That's nothing really. That's in a three-dimensional simulation, which this is not, you would have in the millions probably, at least a million cells. So there we go. You can look at it, and a good mesh is one where the cells are not too distorted from a rectangular or a square shape in this case, with this type of mesh. And let's zoom in, and here you can see, well, some of them look a little weird, but actually they don't look so bad. We can get away with this, I think. And I'm just going to zoom back out. Okay, and there we are. So next, that was pretty easy. Next step, we go to physics, where you can tell it, okay, we're going to keep it as air. It's going to be steady state, isothermal, no temperature changes, and it's going to be turbulent flow. And here you've got all the properties of the air down here, which you're going to need to calculate the Reynolds number of the flow. So okay, so let's say, so here's the density, viscosity. We're going to need that dynamic viscosity, and I think that's pretty much all we're going to need for the Reynolds number. So now we go to boundary conditions. Okay, so boundary conditions, now you just tell it what every boundary is going to be, just as the name says. First you click on this left one here, hit new region, and that's going to be an inlet. So you go up here, and it's an inlet. Okay, so we're going to have the velocity be, let's say 10 meters per second. 10 meters per second, and that's all we're going to need. So we just apply. All right, and then now we're going to do the outlet. It's going to be here, new region again, and you. By the way, I clicked on that boundary, right? So this is going to be an outlet. Outlet wall. Conservative is good. In other words, what comes in goes out. We hit apply, and there it is. Now we just need to specify these two walls here. So click on the top one, then I'm going to hold down Shift and do the bottom one. So they're both, so new region again, and that's going to be a wall, well, but we're going to make that a so-called symmetry plane. That means there's going to be no friction on it, so that it won't, the boundary, any boundary layer developed there is not going to interfere with the foil. All right, so we hit apply for that, and that's it. So now we just have to worry about the foil itself, and we're going to make that a wall also. Okay, so new region again, and it's going to be a wall, and I'm just going to change the name though, just so we can, later on we're going to just need to find it, so I'm just going to call it the wing. Okay, apply, and there we go, we're all set now. Calculation parameters, right? Here you give a maximum number of iterations. Let's up it up to 1,000. We probably don't need this, but I'm just showing off, I guess. So now we go to solver, and we're going to really, it's going to just hit solve. Everything should work fine. Okay, ready? So hit solve, and you'll see there's going to be a graph made here. On this axis you're going to have the residuals, which tell you how close you're getting to the solution. When the residuals get down to 5 times 10 to the minus 6, or over here, the calculations will stop. And here's the loop number here. So here we go, hit solve, and we go. Now you can see the residuals are going to start diving down. Those are all for in the U and in the X and Y direction, or Z and Y direction, residuals. So they're diving down. This is running pretty quickly, and when you do a real life one, this is going to take a lot more to run. You know, hours, days, maybe even weeks. So let's hit OK then. Now you go to post-processing, where you go to look at your results, right? And now the first thing is, let's take a look at our contours of velocity. All right, so I clicked on contours, velocity, show them here shaded, and we're going to show the scale too, so we can know what each color means. Let's put lines in between the colors to make it look even snazzier. And there you go. You can see the plot of the velocity. If you zoom in, you'll be able to see, look, you've got a yellowish color. That's like maybe 13 meters per second on the top. Oh, the flow is speeding up on top of the foil. The flow has to speed up to get around the obstruction. Remember, it was coming in at 10 and sped up to 13, maybe even a little higher, like 14. So if you want to see the pressure field, and let's try to think what you would expect to see. You'd expect to see the pressure lower, and sure enough, yellow is like 43 pascals, right? Whereas these green is much lower, it's like negative 10 pascals. These are gauge pressures, I guess. So there we are. Very good. So now what we're really interested though is well, we could also show the vectors too. That's kind of fun. Also, show them here and apply. And there's quite a few of them. Sometimes you want to reduce them. So let's reduce them by a factor of 32 times and apply. And you know what? Let's get rid of the contours because they're kind of the contours are kind of messing up the apply. So now you can see, you can zoom in now and see them. Let's put a few more in. These are not that many vectors, right? So a reduction, maybe bring it back down to 8, say. Apply. Okay, that's nice, right? So, you know, not seeing much separation here. If you were to incline the angle of attack higher, you would certainly see a lot of separation, but I'm not really seeing much. Maybe, right? All right, so now what we're really interested in is the force on the airfoil. So what you do is you go to Analysis tab up here, and we're going to click now. Remember, on the wing. See, that's why I changed the name so we could find it easily. And there we go. We've got here's the area. This is the surface area of the airfoil, right? 2.04 meters. It assumes that it's 1 meter into the screen. So it's 0.204. But if you want it, the kind of area that we'll need will be the chord times the wingspan. The wingspan, remember, is 1 meter into the screen. It's a two-dimensional simulation. Nothing is happening into the screen, but so we want to get the chord measurement. And the way you can get that is you read it up here. You've got the x-coordinate and the z-coordinate. So very approximately, we can say that the wing is going from here, which is the x minus 2, to about minus 1. So it's almost exactly 1 meter long, this wing is, okay? Almost 1 meter long. So the area, in this case, that we're going to be interested in is 1 meter long by 1 meter into the screen, which will be 1 square meter. In my case, yours may be, no, yours should be about the same. Should be exactly the same. So here, look, we've got, here are the forces, right? And we've got a force of, the total force in the x direction, that's the drag, is 4 newtons. And you notice it's broken up into a pressure component and a viscous component. The pressure component is due to the higher pressure. Let's take a look at the pressure again. Show it. Apply. You've got these high, you've got this high pressures here, like 84 pascals, right? Over here. And whereas in the back, you've got a much lower pressure. So that's a higher pressure in the moving towards the right, which makes a drag, right? But then there's also the viscous component. Let's go back to the analysis. So that was the pressure component. Due to the pressure differences, the viscous component is just due to the shearing that's happening on the top and the bottom along the entire skin of the airfoil. And you can see that's much lower, 0.39 in the x direction versus 3, right? A factor of 10 difference. And in the z-axis, here you've got pressure component. Look how big the pressure component is on the z-axis. 49 newtons upwards, right? So here's your total force in the x, total force in the z. So we'll be able to get lift and drag coefficients just using lift is equal to 1/2 rho v squared a times coefficient of lift. All right, so and then we'll check our results against published values, and we'll calculate those in the class. All right, so once you get your lift force you can calculate your coefficient of lift and coefficient of drag, and also get your drag coefficient and your lift coefficient. That's it. Thank you. Have a nice day. Nice to see you and all that stuff. So Shift F10 stops it.